My talk is in line with the previous one, so it's not so much about research, it's not about cheap labor, it's more about made in Germany, something that is commercially available. Let me briefly introduce the company I'm working for. It's Selex ES, a German weather radar manufacturer. We are based in Neuss, which is between Düsseldorf and Cologne. Our parent company is Leonardo. That's why you have here the Leonardo on our roll-ups and also on our booth in the lobby. In our product portfolio, we have all typical types of weather radars, starting from C-band, S-band, and X-band. We have our own software development. We are having our share, so to speak, in wind shear detection in the aviation framework. And what is more and more important is to integrate other sensors and, of course, to provide the services for our customers. Weather radars is a worldwide business, so our customers can be found around the world. Let's face now urban hydrology. We have heard this already today and yesterday. Specific challenges, impermeable surfaces, a fast runoff concentration, and a dense population and a concentration of assets. So it really is special. And when we talk about flood management, especially in urban hydrology, of course, we have to address all building blocks to really solve the problem or find some good solutions. However, what has been said in the previous talk already, detection is, of course, a key element. And for detection, a sensor like a weather radar is a nice tool. We have a huge aerial coverage. There's a nice spatial resolution, and even though we have this nice rainfall map, we have a high update rate. And for those who operate weather radars, it's nice to do much of the maintenance and management of the sensor remotely. So really impressive sort of sensor here in the framework of rainfall detection. If we look at some installations here, typical C-band or S-band weather radar systems, there are sometimes really nice designs of the outside. However, often inside it's very similar depending on which system is used. Nevertheless, I mean, even here in Europe, we have a nice density of weather radars, but currently and or in the last years, the topic of local weather radars has become more and more popular. So the question is, why is this a current topic, especially here in the framework of urban hydrology? So apparently there are some deficiencies or some issues here with current weather radar networks, and there may be cases when a local weather radar can help. So let's have a look at what could be the reason to go for a local weather radar. Let me start with resolution. I'm not talking about the physical resolution, which is here dependent on the sensor type. Often local weather radars and S-band, C-band systems are provide here similar. I'm talking about the data resolution for the end user. And if your weather radar provider has an update rate, for example, of 10 minutes or a data resolution in terms of your spatial data bin of 1 degree by 1 kilometer, it might be not sort of state of the art. Current standard systems as well as our local weather radars can provide resolution of like 50 to 100 meters, 1 degree down to maybe half a degree. and update rates of 1 minute to 5 minutes, depending on how you manage the system. So what is the effect? If you compare here on the right-hand side, the standard weather radar 1 kilometer by 1 degree. On the left-hand side would be sort of the high-resolution data. And you can see clearly a difference here in the spatial resolution. We can also look at the timing. On the left-hand side, it's a 5-minute update rate. On the right-hand side, it's a 1-minute update rate. It's of course, the sensor was providing data with 1-minute update rate, and the left-hand side was sort of reduced to show how it would be if it's just 5 minutes. So a fast developing storm is, of course, better captured with a higher update rate, even if it's maybe not 1 minute, but let's say 5 minutes. Another issue could be how far is the next weather radar to your city, to your location. If your weather radar is quite far, Earth curvature comes into play, so the measurement is taken at a rather high altitude, which means that we have a bigger volume which we measure. We are sometimes above the freezing level, and this all reduces sort of the quality of your data. Not speaking about maybe some blocking here, if there are some mountains or other things in between your location and your weather radar. What I did mention here on the slide is, of course, the ability to find some data for your location. We know from the US, as it has been said before, we have the free data. In European countries, it can be quite different, so maybe you just don't have the chance to get free or even to get sort of radar data which you can afford. So these are typical reasons why you might consider to have your own radar, but if we look at here a standard C-band with a big tower, it's quite costly. So when we look at, on the right-hand side, a so-called local weather radar, this is our X-band. It's from the sensor itself, it's smaller, that means it's less costly. But as you can see, also from the installation, it's more flexible. You can sometimes just place it on some rooftops, which of course is quite easy. Nevertheless, we should always keep in mind that this comes for a price, and this is the sort of usable range here. Our X-band is a rather powerful one. There are other systems on the market where the usable range is much smaller. So to summarize here, the local weather radar as a sensor, X-band sensor, all components are typically smaller in size, makes it price-wise better. We have less costs for the infrastructure. We are often more flexible in the siting and placing the sensor, and of course operation, power consumption, spare parts, and often also permissions are easier to achieve here. Let's look here at some of our permanent installations, also adapted to the individual use here. But if permanent is not something you like, you can also have the mobile version, which allows even easier relocating of the sensor. But here I want to stress, it's not only about the sensor itself. It's not about just buying a weather radar and being happy with the data. There are challenges starting from where to place the radar. It's about maintaining the sensor itself, sort of calibration, we have to carefully consider the operating mode, update rate, etc. And what I will talk about in the next slides is the data processing. Just the raw data is often not enough for hydrological use. So to guarantee that we have at the end some nice rainfall maps, we have to have some processing steps. I want to just mention here some as example. For example, attenuation. X-band systems are nice, they are smaller, but they face more attenuation. That means the signal is attenuated when it travels through rainfall. And with dual polarization systems here, attenuation correction is quite nice. However, it must be done, and even though here this correction of more than 5 dB seems small just when we compare the colors, rain-wise it can just be more than 50% of correction. So this is really important. Unfortunately also the weather radar, or each weather radar picks up signals not only from our rainfall, from our weather, it picks up a lot of other signals like signals from the ground, from sea surface, insects, and other objects. So we need often, for hydrological purposes, to remove those echoes, otherwise they might give false alarms. And for this we have this dual polarization technology. Here's a nice sketch here from NSSL showing that dual polarization allows us to sort of measure the diameter in vertical and horizontal orientation of our targets, and this helps us to identify the targets, classify and remove if necessary. It also allows us to identify different kinds of hydrometeors, like raindrops, like liquid rainfall, snow, hail, graupel. This can be also additional information for your operation here in this framework. And another step is, of course, to convert what we measure here in terms of reflectivity, so that what the radar sensor detects, and to convert this in rainfall intensity. This is sometimes more complicated than is expected. We have, or nowadays we can use this dual polarization data to improve this. We have also often to mitigate influences of the melting layer, which can be seen here as radial structures, as concentric rings, sorry, and to really have something that can be used as input for your models. Nevertheless, although the sensor might be latest state of the art and we have dual polarization and all that, additional ground truth data can often improve the data quality. Here I have some examples for rain gauges. We heard in the previous talk about dysdrometers. Both can be used. However, whenever you use ground truth data and you use it for adjustment, it's important to assure that the quality of this data is good enough, because this will be your reference. If your reference is not giving you the truth, then it can be critical. So quality control is of course important here in this framework. What does adjustment mean? Adjustment means we use still our radar map. So we have the high resolution, we have the coverage, but we adjust the, in this case here, the accumulation value to a level of our ground sensor. And this is done here, in this case, spatially distributed. So Now we have our detection, we have our rainfall maps, but it's currently only a detection. Other steps could be the nowcasting. So use the information of the radar to do some forecasting. We can do this based just on the radar data. That means we look at the current scan, we look at the previous, and from the movement of our rainfall field, we can guess sort of what it will do in the next few minutes, 30 minutes to 60 minutes, and we will extrapolate the current movement into the future. It's limited in time because rainfall changes over time. So to extend this forecast range, we have the option to include NWP, numerical weather prediction data. In our example here, we can extend forecasts up to 5-6 hours. Of course, the numerical weather prediction will provide longer forecasts. This is here data from the Polish Met Service. Thank you for sharing this data. It's just the radar-based nowcast. That means on the left-hand side, we have a 1-hour forecast just based on the radar measurement. On the right-hand side, we have the verification. That means the radar network data from sort of +1 hour. And in stratiform conditions, and especially if you have a full radar network, of course, this can work quite well. The next slides are about our implementation of the STEPS algorithm. STEPS was developed by the UK Met Office together with the Australian Bureau of Meteorology. It's an ensemble prediction, and we hold a license for this and have integrated this into our software. And here I want to acknowledge my colleague, Dr. Ronald Hannesen, who has provided here these slides for my talk. On the left, this is again an example here from the Polish radar network. On the left-hand side, you can see the input from the numerical weather prediction. It's not directly the output of the model. It's sort of rescaled to the radar grid. In the center, you have the combination of radar data and NWP as provided by this STEPS implementation. And on the right-hand side, you have the observation. So just the radar data. And this is sort of the current time step. And I now go into the future. And what you can see here is that the weight of the radar data will decrease in our sort of forecast here. This would be the forecast which you would receive from the system. And it will, of course, the influence of the NWP will increase from time step to time step. And then, of course, it's more or less about the NWP. Last but not least, I want to talk about data interfacing. Operators of weather radars know we have the sensor somewhere. We need to get the data into our center, into our data processing. We need communication for this. We also want to export our data for other systems like our hydrological models or different kinds of decision support systems or dissemination systems. So it's important to really improve here standard formats to have conversion available. And in our software, we have different options here for this export, and we try to keep this updated as possible to allow here customers to easily share and use the data. Okay, to summarize, a local weather radar can make sense if the the conventional radar network does not provide the data sort of in the quality or for the price that you expect. However, if you deal with your own radar, it's not just about buying a sensor. You need some careful assessment of where to place it, how to operate it, and of course, how to adjust the data processing so that at the end, the data is of the desired quality and you can use it in this framework of urban hydrology. Okay, with this, I thank you, for your patience here.
Thank you for your presentation.